and also for braving the weather to get here. I know we're all on fire, so that was very brave of everyone. Today I'll be talking about accelerating production machine learning with MLflow. So as we know, machine learning development is complicated. To give a sense for this, a typical machine learning pipeline looks like something like this. You take raw data, you want to ETL it or featureize it. This is data prep. Then you want to do some sort of training to produce a model, and you want to deploy that model to production. Score it, produce a REST API serving layer, run it through Spark, that kind of thing. And then you might, as you get new data, want to reiterate this process and do it again. There's a lot of different frameworks for each of these components. So for the raw data, you might have any sort of storage system, S3, Hadoop, Kafka. Data prep, there's a lot of tools out there as well. And so both for like the ETL as well as for the creation of feature engineering. Training-wise, there's also a ton of different tools. So from scikit-learn, PyTorch, TensorFlow, all these are things at your fingertips. And then deployment, you might go for Kubernetes or Spark or Azure ML or SageMaker, these kind of things. You might deploy to any of these. And so one thing to note, kind of interesting, in many parts of like engineering, we want to pick like one tool and then like kind of deal with the problems with that and then just make it work. But in fact, for a lot of machine learning workloads, your goal is to sort of just maximize, to get the best kind of results. So that might be the highest accuracy, or it might mean some mix of accuracy and explainability, or some mix of accuracy and performance. And so in order to do this, you actually want to go through and just try out as many different kinds of models, as many different frameworks as possible, both in the featurization data prep space, as well as the training space. Okay, so we actually want to try and leverage as many of these as possible. In addition to sort of trying different ones, like tuning which kind of framework we use, all of these have different hyperparameters, for example, for the training side, or different features that you can engineer and build off of for the data prep side. So we have to kind of iterate and do a lot of work in order to optimize that. And then as we kind of do this multiple times, we need to keep track of how things are changing, and we need to sort of scale up every component. And after we do all of that, and we have a nice, successful, scalable model, we have to be able to share it with our coworkers, and then, over time, be able to manage this model. So that's kind of the notion of exchange. So this is all, the very typical machine learning development workflow when you want to productionize a real model. Now, as a data scientist or ML engineer, what you really want to spend your time doing is like the feature engineering, potentially, or maybe just the training and the moving to production stage. You don't want to spend a lot of time in sort of the data prep, or like the raw data, the deployment, or like the scaling, or all these other things. So what's kind of the state of the world today? So the state of the world today is that there exist these systems that big companies have produced that are doing a lot of machine learning. So Facebook, Uber, Google, for example, LinkedIn as well. I'm sure Twitter has one too. That are very customized to their internal tooling. And so these are great because they standardize the entire data prep, training, and deployment cycle. And so if you work within this company, within this platform, you can move very quickly, you can share your results, and that's awesome. But the problem is, two problems. One, oftentimes they'll be specific to a small number of algorithms or frameworks that this team wants to support and has the capability of supporting. And they'll also be tied, of course, to one company's infrastructure, so it's not broadly usable. So kind of the problem statement of MLflow is, can we provide similar benefits that these tools get at these companies in an open manner that everyone can leverage? So MLflow is an open source machine learning platform. One of the goals is to work with any existing machine learning library and language, and to be able to deploy it and run it anywhere. So on any cloud, locally, whatever, and to be able to scale up to big data. So we actually, this is a relatively recent product. We launched this June, open sourced it. Already we have 57 contributors throughout numerous companies. And there's a lot of new features that have been introduced since its inception. So in this talk, I want to talk about kind of the architecture of MLflow. I want to give a brief demo, and then kind of talk about announcements and future direction of MLflow. And that's it. Okay. So to start with, how does MLflow work? How do we kind of take this complex pipeline that we want to build and break it down to different components? So there's three major subcomponents within MLflow that we kind of broke this problem down into. So the first is tracking, projects, and then models. So for the tracking piece, this is how, as you're iterating and running experiments, how you capture the code and the data and the results that you've done, so you can compare them now and later in the future. Projects is a way to package your code in a way that can be and dependencies, so that not only can you run it, but other people on your team can also rerun these workflow steps. And finally, models is an interface between the creation of the training step and the deployment step. And so I'll walk through kind of how all of these work. So to give a sense of kind of why we're talking about this, let's first talk about how we might do model development without MLflow. So this is today. So I might have, this is a very simple, very obvious problem. I have some text. I extract it into n grams of some number of n. I train some model on it, so that's kind of abstracted away. And that model maybe has a parameter such as learning rate. And then I compute the accuracy. And in this case, I just print it and then pickle it out to a PKL file, which I could then load back in to do inference somewhere else. So this works great. I can just try out a bunch of different n, a bunch of different learning rate, and pick the best accuracy. And this is kind of like what a lot of people do, and it makes a lot of sense. It's a good starting place. But as we kind of talk about change over time, it doesn't really age very well, this piece of code. So for example, if I expand my input data, how do I then compare the new results to the old results? Or if I want to tune some other parameter, now how do I, the same question arises. Oops, back. Or if I upgrade the library and I want to see how that changes things, or if I just want to change other parts of the code and want to compare two entirely different sets of code. Now that this n and LR and accuracy may not be sufficient to do that. Additionally, so that's kind of the development side. Once I've finished developing my model, I have a great model, I want to deploy it. So typically what happens is that a data scientist will create the model, and that will produce some amount of code, some amount of models, and they'll ask the production engineer, please put this in a REST server, or please do batch inference on our production data, and they kind of want to hand it off that way. So in today's world, this looks a lot like the data scientist might produce a scikit-learn model, please deploy this, or a Spark model, or R, or TensorFlow, or just a random archive idea that they've implemented. And so the production engineer has to do something special for each one of these, and that's quite a headache, and it increases the burden and the inefficiency between these two parts of the organization. So we can fix this with MLflow. So we're going to replace the print and pickling statements with this notion of MLflow log param and MLflow log metric and this notion of log model. So once I just log the parameters that were input. These are the inputs to my program. The metrics that were output, like the score, and then the actual model itself, because MLflow has a scikit-learn package, as it does for TensorFlow and all these other things. And we're just going to log that out as well. And so now I can just open up locally this MLflow UI, and I can track these parameters, metrics, and output files, and the code version, in fact, of this code itself, and just search through it. So you can see here, like this is an example of the UI. I can sort by various components. I can find the best accuracy. I can click into one, look at the actual plots and results that came out. I can say, okay, this was the best one, and just put a note. And so this is a way I can sort of collaborate and view runs across my little experiment here, either now or in the future. Additionally, I can compare runs. So I just want to try to find how different runs are different. And so this is just one example representation where you can just do a scatter plot against two different axes and just kind of see, for example, the dependence of these two metrics in this case. So that kind of gives an overview of how MLflow provides tracking utilities as you're trying to train and compare your models. Additionally, so the next problem is projects. So I might have code and dependencies and config, conda packages, Python packages, jars, whatever. And I know how to run this locally, but I want to have someone else on some other team also be able to run it locally. Or I want someone to be able to run it on some remote cluster. And so projects provide a way for you to specify and operate in an environment where you provide your code, dependencies, and config, and then can use it in these other environments. Finally, the last component of MLflow is models. So models allow you to, so rather than having this n by n problem of saying you've produced a TensorFlow model or you've produced a scikit-learn model, and then you want to deploy that scikit-learn model to Spark or that TensorFlow model to Azure ML, instead of having this problem for each trained model and each deployment tool, instead you can say, how can I create an MLflow model from my training application? And then as long as your inference code can take in an MLflow model, then you have to decouple these two. So you only need to write one connector for Spark or one connector for Azure ML, as opposed to n for each individual training program. And so I'll kind of show an example of that during the demo. Once you have this kind of model, now instead of saying, please just deploy this scikit-learn or R, et cetera model, you just say, please deploy this MLflow model. And then you can just get it into a REST server or Spark or wherever. Okay. And then you can update it over time, for example. Cool. Okay, so now just to kind of show a demo of this. Right. Cool. So this demo I'm going to be showing using a notebook. This is actually part of the open source examples though, so you can actually just download this code locally from the MLflow repository, and you can just play with it and run the entire UI, the entire thing locally. So there's nothing specific to notebook environment, or in this case, the Databricks environment. So the data we're working with today is going to be this wine data set. So there's some very serious researchers at a university who collected for 4,000 different bottles of wine. They measured some of the physical properties of them, like the acidity and alcohol and pH, this kind of thing. And then they had 3 people taste test it. And then they took the median score of those 3. So this is very serious research. It's very important to the progression of society. And so the goal here is, can we take these physical properties, these chemical properties, and predict the quality that someone would estimate from it? So so that's our data. So we're going to use scikit-learn for this. And so I'm just going to import some stuff. Here you see we're reading the data. We're going to split it into, let's say, a 25-75 training and test split. And we're just going to say, okay, all of the features we're going to use is everything except the quality. So all the features you see above. And then the thing we're trying to train on is quality. And then we see here we're going to be using an elastic net model. So elastic net, if you aren't familiar with, is a kind of linear regression. So for every one of these features, we're just going to try to find some coefficient that matches it. And additionally, we have this extra regularization term based on alpha, which can basically decrease the tendency to overfit on this model. So it won't be quite as good of a fit on the training model, on the training data, but hopefully it's a better fit on our test data. And additionally, there's an extra parameter called L1 ratio, which is related to which regularization term we're using and how much weight to give it. Anyway, at the end of the day, there exist these 2 hyperparameters that have some effect on how well our model generalizes and how well it does. So we're just going to use scikit-learn's elastic net to train it. We're going to predict the results and then evaluate kind of how it did. And so we can kind of just run this. And we see here that we get like, a root mean squared error of 0.81 in this case. And I can just kind of rerun and change this around a little bit. So 0.8. So obviously I'm trying to get a lower error, maybe 2.77. Okay, so I got a little bit lower. But now that I've kind of run this a bunch of times, I might have a hard time looking back and saying, okay, which was the best one overall? Or as I change parameters over time, kind of what was the best? So what I'm just going to do is I'm going to add in, first going to import MLflow. And so I'm just going to take this code and wrap it with some useful logging metrics. So I'm going to say start run. Indent. And in addition to these prints, I'm just going to have, actually I'll just replace the prints with MLflow.logparam. So we'll start by logging the alpha value and the L1 ratio. And then we'll just log the metrics as well. So we're going to log the root mean squared error as root mean squared error, and the metric mean absolute error as mean absolute error, and the R2, R squared. And additionally, one last thing we're going to log is the actual model itself. So this LR is actually a linear regression model that we can then read back in. So I'm just going to call it sklearn.logModel. That. And so that will run. Cool. And so I'm going to run this a few more times, just with different parameters. 0.3 maybe. 2. Just try some. Cool. And then now I've run this, I can now go to the MLflow UI, refresh. And you can see the runs that I've generated are here. And let's say I've taken the root mean squared error, and I'm kind of sorting, well, descending. I probably want to sort ascending to get the smallest. And we can see here that, for example, the alpha 0.1 and L1 ratio 0.2 was actually the best among these different things. And so I can actually click in and kind of see more information here. For example, I can show you the ML model file type. And you can see that this, for example, is a scikit-learn model, and it's also loadable directly into Python. So that's the notion of an ML model. One other thing I kind of want to showcase here is that in addition to these parameters and the metrics, we also have the code here. So for example, let's say I actually just change my code to say, okay, what if I just try training on more data? Maybe that will help. So I'm going to change the test size to 0.1. I'm going to rerun that. And then let's say I'm going to pick the same parameters that were the best. So 0.1 and 0.2, let's say. I'm going to rerun that. All right, refresh the page. Okay. Actually, in this case, it didn't, wait, maybe I did not do something correctly. That looked good. Okay, actually in this case, changing the test size did not help at all. So they're identical, but yeah, okay. Anyway, nevertheless, I can look at the actual revisions. Sorry, 1 second. So if I click on the actual source, I can see the different revisions of code. So for example, in this one, I can see that the test size here was 0.1 and that the test size here was 0.25. And so just kind of like associated with each run is not only the metrics and parameters, but also the actual code that executed here. So I can go back in time and kind of restore to this and run it, for example. Cool. Yeah, I guess there was a slight reduction in the mean absolute error and an increase in R squared. Cool. Okay, so once I've completed my model training, now I could, as maybe a different engineer in a different environment entirely, I want to do inference using this model. So I have a good model and I have new data that came in, and I want to kind of check out how well it's doing. So I'm going to plug in my run ID. And so you can see the code that we're doing here. To start with, this one is very specific to scikit-learn. It says load back that scikit-learn model, and then just predict based on this kind of very specific wine feature set. And you can see that it predicted for this one quality of 5.57. I can also do this in Spark of just loading it, of saying MLflow pyfunc Spark UDF. And then this is actually pyfunc, so it didn't actually require anything about MLflow itself, or sorry, about scikit-learn itself. And using the same run ID, I can then take my original data frame, which is this guy up here, and I'll supplement it with the actual predicted values. Okay. And so we can see here that we have these quality metrics along with the actual predictions for each quality. Okay, and so basically that was kind of an example of how to do batch prediction using the model that I trained somewhere else in the same notebook in this case, and predicted here. Okay, so that's just a demo of how we can use MLflow to take an existing workload and supplement it in a way that we can kind of decouple both the deployment, so the training and model inference parts, as well as kind of help compare and evaluate the metrics over time and go back and look at how things went. Okay. So just to kind of give an update on kind of how this project is going. So since the release in June, we've added a lot of model packaging formats. So for example, we support MLlib, H2O, TensorFlow, PyTorch, Keras, and we're adding any new ones that as people add them. There's a storage backend for these artifacts, and that supports basically the three major clouds at least, as well as SFTP. And in addition to the Python API, we have Java and R APIs as first-class citizens. Of course, it's also API. In general, we're API first, so the REST API is always good and up to date, but these are just kind of convenient wrappers in these languages. And additionally, we have new examples, so it's easier to get started with. There's a lot of documentation on that, and improved UI features for this help of comparing and visualizing results. So in conclusion, workflow platforms can greatly simplify ML development, improving usability for both data scientists and engineers. And MLflow attempts to do this for all machine learning workloads. So you can get started at mlflow.org. Cool, thanks. Yeah, so questions?
Does it work with Scala API?
Yes, so it works with Scala, but the API, the current client is actually it's Java first. So I mean, we implemented Java, so it's more natural to use it from existing Java workloads as well as Scala workloads.
Does it work only in Databricks UI or?
No. So yes, the UI is completely open source, so you can just download it and call it MLflow UI locally, and actually launch as a server. And you can either run that server locally or you can run that server remotely and just authenticate it to it that way.
And you didn't say anything about deployment. So once we have models, let's say imagine scikit-learn.
Yeah.
And we want to deploy it to a large cluster with 5,000 processors.
Yeah. So actually, I did actually show that. So maybe it was a bit subtle. So the deployment could mean multiple things. In this case, I was deploying it to Spark, and so this is actually running. This could run in parallel on any number of machines, either in a batch format or in a streaming format. And so I was actually loading it as a UDF. So now this is just a UDF, and so I'm calling with column, where I'm adding a new column called prediction that actually takes in from the data frame. So just to kind of show that again. So the input df was all of the features, and the output I added prediction. And so that is actually running across a cluster.
But does it depend on Spark in any way?
No, so yeah, so good question. So the question is, like, what does deployment mean? So one thing deployment can mean is you want to do batch inference across many machines. In this case, MLflow comes with like the ability to convert your model into a Spark UDF. It could also mean, though, for example, just running it on one machine. And so we also have a way of just loading it back into like Python itself, for example, and then just serving it. We also have a way of serving it as a REST API endpoint. So then you can just deploy it to Kubernetes or SageMaker or Azure ML, whatever you like, just as a REST API endpoint.
I could use it for logging and what you call versioning my modules and on this side serving.
Exactly. Yes. So the tracking side is about logging and versioning your models, and the serving and the deployment side is both about serving as well as other kinds of batch inference or streaming inference.
I'm seeing a notebook here. Is this the kind of a way to define a workflow for this?
It's a good question. So actually, not necessarily. So Git is actually a pretty good way of defining. So for example, just to show the, so this example is actually pulled from this one right here. And you can see here in our train.py, it's very similar code, almost identical. The advantage of Git is that you can kind of check in it all at once and kind of like point to the actual Git repository. And I can actually run it from a Git repository, in which case it will include the commit history, like the actual commit ID. So what you can see here is in this UI, this source is a notebook and it actually points to the revision. But if I ran it locally from like a Git repository, it would actually be the Git hash instead. One advantage of that approach is that if you run like this Python file, it's like all or nothing. Whereas one weird thing about a notebook is that I could have actually run things in a different order, and it's not necessarily obvious which order you ran it in. So it's a kind of subtle, slight weakness of notebooks as we have them today. One thing to also note here, actually, I didn't show this because I was running it in a notebook instead. This is the notion of a project. So it's very simple. You can see it just says, so we're not specific to Python or Java or Scala or whatever, but it just calls Python train.py. But I guess one thing I didn't mention, I know the Scala conversation came up. Most data scientists do use Python and Python-based libraries. The main exception to that is Spark for MLlib. Almost nothing else is in anything other than Python or C++, as far as we found. But that said, this is not specific to Python, this particular part. You can define parameters. You can define a conda YAML file. So this includes, this is like, conda is a way to package Python dependencies, so you can select specific versions. And so now this is reproducible. So if I just come into this directory, call MLflow run, it will activate, it will download these packages in a virtual environment. It will then run it there. So similarly, you do a Docker container. We actually don't have a way of doing jars right now, because that's a little bit more complicated. How you have to inline SBT or inline Maven or something in this. But this is the notion of a project which allows you to reproduce this across multiple machines. Other questions? Cool. Well, thanks.